Grab your thermal blankets and maybe a theoretical physics textbook, because today we are staring down the cosmos's most fundamental mystery.
We are.
We're talking about black holes, but not just as astronomical oddities. We're treating them as the ultimate physics laboratory.
That's right. For this deep dive, we're synthesizing the spectacular insights found in black holes. The Key to Understanding the Universe by the acclaimed physicists Brian Cox and Jeff Forshaw.
And they make this, I think, really compelling case that these objects are not just cosmic vacuum cleaners.
Right.
They're the critical nexus point where our two greatest yet, incompatible theories of reality collide.
General relativity and quantum mechanics.
I love that approach. It transforms black holes from merely destructive phenomena into profoundly generative ones. Their existence forces us to confront the very limits of what we know.
Exactly. And Cox and Forshaw argue they hold the ultimate key to decoding the universe's past and, maybe more importantly, its future.
They're great communicators.
They're masters at clarifying these ideas. I mean, Cox, famous for his work as a particle physicist and popular science communicator, and Forshaw, his collaborator. They managed to take concepts that would normally require a PhD in mathematics and just make them approachable.
So what's the central thesis?
Their thesis is that black holes provide the most rigorous, elegant proof of general relativity, or GR, while simultaneously exposing the deep, necessary cracks that only a unified theory, a theory of quantum gravity, can possibly fix.
And before we plunge in, let's ground ourselves with the foundational philosophy that kicks off this whole discussion. That line from John Archibald Wheeler.
Oh, it's the best.
Space-time tells matter how to move. Matter tells space-time how to curve.
Everything we discussed today stems from that beautiful, elegant concept.
Mm-hmm.
We're going to begin by understanding that curve.
Okay, let's do it.
Chapter 1.
So our starting point really is where Cox and Forshaw make a huge deal about the inherent beauty of general relativity. When physicists talk about GR being beautiful, what do they even mean by that?
Well, they're genuinely moved by its elegance and its economy. It's a theory that says gravity isn't some mystical force pulling objects together from a distance.
Right.
It's a purely geometric phenomenon.
Think about that for a second. The fact that the most fundamental force shaping the cosmos, the thing that keeps your feet on the floor, is essentially just a description of curvature in a geometric field.
That's profound. And the core equation describing gravity is notoriously complex, relying on some really arcane mathematics to calculate the precise curvature of space-time in any given scenario.
Especially for, complex arrangements of matter and energy.
Oh, absolutely. The complexity of the math versus the simplicity of the underlying idea. Gravity is curvature, but calculating that curvature precisely, that's the hard part.
Right. And here is where black holes enter the scene as a physicist's dream object.
They really are. For almost every other scenario in the universe, say two galaxies colliding, the mathematics of GR become virtually intractable. You need approximations, you need huge supercomputers.
But a black hole?
But a black hole, specifically the region outside the event horizon, is characterized by such perfect, simple symmetry that its geometry allows for precise calculations of space-time curvature.
They are, mathematically speaking, almost too perfect.
Exactly.
Yet, for us, understanding that geometric perfection is difficult because we run head first into the visualization challenge.
Totally. We live in 3 spatial dimensions, plus 1 dimension of time, 4-dimensional space-time. But our minds, and, certainly our whiteboards, are stuck in 2 or 3 dimensions.
It's like trying to perfectly map the Earth, a sphere, onto a flat sheet of paper.
You can't do it without distortion. Physicists have to rely on dimensional simplification, usually depicting just 1 spatial dimension alongside time to represent curvature.
So when you see those famous diagrams of a bowling ball depressing a rubber sheet, that's what they're doing. They're simplifying the situation massively.
Massively. But the principle is sound. The goal of that simplification is to minimize distortion while highlighting the essential feature, that mass creates a dip or curvature, and other objects simply follow the straightest path available within that curved geometry.
And black holes just represent the steepest, most profound dip possible.
The absolute steepest. So that's chapter 1, which brings us to chapter 2, warping space-time.
This inherent geometric truth was discovered remarkably quickly after Einstein published GR in 1915. This takes us to the truly incredible story detailed in the sources. the breakthrough of Carl Schwarzschild.
It's a phenomenal piece of history. In 1916, while serving on the Eastern Front of World War I in the German army,
In the middle of a war.
in the middle of a war,
I see.
and tragically, just months before he died of a rare skin disease, Schwarzschild found the very first exact solution to Einstein's massive complex equations.
That's just wild.
And this solution described the geometry of spacetime around a single, non-rotating, spherically symmetric star.
And Einstein was reportedly blown away, not just by the speed of the solution, but by its pure mathematical elegance. It was a huge early validation for GR.
It was. It provided slight but measurable improvements over Newtonian physics in predicting things like the subtle precession of Mercury's orbit.
But the real revelation, which they didn't fully recognize at the time.
Not at all. The revelation was that this solution mathematically implied the existence of a region where the gravitational pull became so extreme that nothing could escape.
The black hole.
The black hole. Schwarzschild had essentially provided the blueprint for the geometric reality of these objects.
To really grasp what Schwarzschild defined, we need to understand curvature intuitively. The sources use some great analogies. Let's think about that old high school geometry staple, the Pythagorean theorem. A squared plus b squared equals c squared.
Right. Works perfectly on a flat plane.
But try to measure the distance between Buenos Aires and Beijing using that formula, treating the Earth as flat, and you fail spectacularly.
Your distance will be completely wrong. Because the space you're measuring isn't flat. The Earth's surface is curved.
So the shortest distance isn't a straight line, it's a curve along a great circle route. So how do we measure that curved distance accurately?
You have to measure it locally. You wouldn't use one massive straight ruler spanning the globe.
Yeah.
You would use numerous small flat rulers, approximating the great circle curve with many tiny straight segments. And this is key to GR. Locally, space-time always feels flat, which is Einstein's equivalence principle. But globally, over astronomical distances, mass dictates a pervasive curvature.
And the sources bring in the wonderful visual example of the Montreal biosphere. It looks like a perfect sphere, right?
It does. But it's constructed entirely from thousands of small, flat, triangular panels. It shows how complex curved shapes can arise from simpler, locally flat geometry.
And that's the parallel to space-time.
Precisely. When you're near a star or planet, space-time is only slightly curved. When you get near a black hole, the triangles of space-time are warped and stretched almost beyond recognition, but the underlying geometry remains precise.
So after the first two chapters, the foundational takeaway is clear. Gravity is not a force. It is the physical manifestation of geometry. Mass warps space-time, and that curvature dictates the paths of all things, from light to planets.
Fully embodying Wheeler's powerful concept.
Okay, so that geometric elegance takes us into Chapter 3, the physical reality of it all.
Real black holes from collapsing stars. If GR describes the curvature, the next logical question is, where do we see this phenomenon in the real universe?
And this moves us away from abstract math towards stellar collapse. The history here is fascinating because black holes were long dismissed as purely theoretical.
Yeah, even Einstein, who provided the underlying theory, was skeptical that such a collapse could actually occur in nature. They were regarded as mathematical curiosities, not physical objects.
Which makes the subsequent validations so much more powerful. Cox and Forshaw highlight the awe of physicists like Subramanian Chandrasekhar.
He studied the solutions describing rotating black holes, the Kerr solution, which were far more complex than Schwarzschild's non-rotating case. And Chandrasekhar was struck by the fact that the mathematical simplicity of the solutions, once found, provides the absolutely exact representation of untold numbers of massive black holes that populate the universe.
That moment, when the beauty pursued in mathematics reflects a profound, universal truth in nature, that's what scientists live for.
It's everything. It confirms that GR is not just a nice theory, it captures the essence of reality.
And in terms of how these things form, the first legitimate theoretical framework for stellar collapse came from J. Robert Oppenheimer and his student Hartland Snyder in 1939.
A simple model, based on a pressureless, perfectly spherically symmetric star collapsing under its own gravity.
And this model showed that once the star shrinks past a certain radius, the Schwarzschild radius, the geometric singularity predicted by Schwarzschild's math becomes unavoidable.
The collapse doesn't stop. It spirals into an infinitely dense point.
Now, what makes these resulting objects so spectacular and yet so chillingly simple?
It's the no-hair theorem.
This is such a great phrase, coined by John Wheeler. It suggests that all the complex history of the progenitor star, what elements it was made of, if it was bumpy, if it had magnetic fields, all of that hair is
Yes,
shaved off.
exactly. The theorem asserts that black holes are the simplest macroscopic objects in the universe. They're entirely characterized by just three properties.
Mass, electric charge, and spin.
That's it. Anything else is shed or swallowed up.
Wait, how can nature be so utterly efficient? If a star collapses, it was full of intricate patterns, atoms, rotation. Where does all that detail go? Is it truly erased?
It's hidden and radiated away. Once the stellar matter crosses the event horizon, it contributes only its mass, charge, and angular momentum, or spin, to the overall black hole structure.
So all the complex information about its composition and internal structure is then shielded from us by the event horizon.
And the external universe sees only those three numbers.
So the outside geometry, the space-time described by Schwarzschild or Kerr solutions, is defined purely by those three characteristics, oblivious to the complexity of the matter that created it.
And this simplicity leads to incredible stability. Research, notably by Richard H. Price, confirmed this perfection. If a black hole is disturbed, say a small planet or a stream of gas falls in, temporarily making its shape slightly irregular,
It fixes itself.
it quickly settles back down. It radiates away those imperfections or wobbles in the form of gravitational waves.
Wow.
These ripples in space-time carry off the excess complexity or asymmetry, allowing the black hole to quickly reassume its perfect, mathematically defined shape.
A state of oblivious perfection, as Cox and Forshaw describe it.
The lesson of this section is that black holes are the ultimate physical manifestation of GR's mathematical simplicity.
Okay, so that theoretical perfection, the pure, simple geometry of the black hole, held up for decades until Stephen Hawking threw a major quantum spanner in the works.
A huge one.
So this is chapter 4, Hawking radiation.
Hawking's groundbreaking discovery in 1974 fundamentally broke the classical view of black holes as purely black voids. He showed that they are not perfectly black, they emit radiation,
And if they emit radiation, they are losing energy, which means they must possess a temperature.
and that insight forced the realization that black holes behave like thermodynamic entities.
This was revolutionary. It bridged the geometry of gravity with the physics of heat and disorder. It led to the establishment of the 4 laws of black hole mechanics.
A direct and profound parallel with classical thermodynamics established by Hawking, Bardeen, and Carter.
Let's elaborate on this analogy because it really solidifies the bridge between GR and quantum physics.
Okay, so the zeroth law states that temperature is constant across a thermal body in equilibrium. For a black hole, this is analogous to what?
The surface gravity, kappa, being constant across the event horizon. Surface gravity is essentially how strong gravity is right at that boundary.
Okay, and the first law relates changes in energy to changes in temperature and entropy. For a black hole, adding energy, say, dropping mass, increases its entropy. And this change in entropy is precisely analogous to an increase in the black hole's surface area.
Wait, let's pause there. That is a massive leap. Entropy, which is a measure of disorder or the amount of information stored, usually scales with the volume of an object.
Right.
Yet for a black hole, it scales with the area of its surface. That completely flips our understanding of dimension.
Absolutely. The entropy scaling with area is Bekenstein's huge contribution, and it's the first real hint that information is encoded differently here.
Okay, so what's next?
And then we have the second law. The total entropy of the universe always increases. For a black hole, this is analogous to the total black hole horizon area always increasing. You can never decrease the total area.
And finally, the third law. Temperature can't fall to absolute zero.
Which is analogous to surface gravity not being able to fall to zero, a state that would require infinite energy, much like trying to cool anything to absolute zero.
So these laws confirm the profound connection. But the huge question remains. How does a black hole emit radiation if nothing, not even light, can escape the event horizon?
This is where the deterministic world of classical physics breaks down and quantum mechanics takes over.
This relies entirely on the reality of the quantum vacuum. And I find this concept so unintuitive for most people because the word vacuum implies nothingness.
It is the most misleading term in physics. The quantum vacuum, according to quantum field theory and the Heisenberg uncertainty principle, is anything but empty. It is a churning, bustling sea of fluctuating energy.
Filled with what?
Virtual particle-antiparticle pairs,
Yeah.
like an electron and a positron, constantly popping into existence, borrowing energy from the vacuum for a tiny fraction of a second, and then annihilating each other to repay the energy debt. They're constantly fluctuating in and out of view.
Like a cosmic high-frequency loan system.
Exactly. Now, picture this process happening right near the black hole's event horizon, where space-time curvature and gravity are violently extreme.
The black hole's immense gravity acts like an energy source.
Precisely. The immense gravitational field magnifies these quantum fluctuations. Occasionally, one of these virtual pairs pops into existence right on the boundary. One particle of the pair, say, the antiparticle, falls into the black hole.
But the other particle escapes.
The other particle, the real particle, manages to escape to infinity, fueled by the energy supplied by the black hole's gravity.
So the black hole essentially consumes the virtual antiparticle, turning the other half of the pair into a real, observable particle.
And since the black hole is supplying the energy for this process, that means the black hole is losing mass and energy. That escaping particle is the Hawking radiation.
And because it's a random quantum process, the radiation is thermal and featureless. It's like heat radiating from a normal hot object.
Exactly. It carries energy but not specific information about the quantum state of the matter inside the black hole.
This single process carries the most profound implication of all.
That gravity itself, in this quantum context, might not be a strict determinant force derived from smooth classical geometry, but rather a statistical law. It introduces inherent randomness into the geometry of space-time.
This is the first unavoidable hint that we absolutely need a theory of quantum gravity to reconcile the laws.
Which sets the stage for Chapter 5, Spaghettified and Vaporized.
This is where things get really contradictory.
The conflicts inherent in trying to unite GR and QM manifest themselves dramatically here. Black holes expose profound contradictions that depend entirely on the observer's reference frame.
This is the moment in the material where it stops feeling like general relativity and starts feeling like inception. Cox and Forshaw detail 3 radically different experiences of reality near a black hole.
Let's start with the most intuitive case, the freely falling observer or the infaller. This person has decided to jump in.
Okay, according to Einstein's general relativity, specifically the equivalence principle, locally, space-time feels flat. So at the moment they cross the event horizon, what do they experience? Do alarms go off? Does the universe suddenly look different?
No drama at all, because GR dictates that gravity is a curvature. If you are in free fall, you are following the straightest possible path in curved space. You wouldn't feel the gravity locally.
So they just float across?
They might look at their watch, cross the horizon, and genuinely feel nothing spectacular. They validate Einstein's theory perfectly.
But they are still doomed, not by the crossing, but by what waits deeper inside.
Exactly. As they approach the singularity, the extreme difference in gravitational force between their feet and their head becomes catastrophic. This is the tidal force.
You need to paint this picture vividly. What does the tidal force actually do?
It stretches and compresses. Imagine the gravity pulling on their feet is perhaps 1,000 times stronger than the gravity pulling on their head. That massive differential force stretches them vertically and compresses them horizontally.
The atoms are pulled apart.
This is the terrifying process of spaghettification. They are stretched into a long, thin strand of matter before hitting the singularity.
Okay, so that's the GR perspective. Painless crossing, painful spaghettification. Now let's introduce the second character, the accelerating observer.
This observer is desperately trying to stay put. They're using rocket boosters to hover just 1 millimeter above the event horizon, resisting the pull of gravity.
So they're accelerating. What do they see?
The vacuum fluctuations we just described, the virtual particles, are magnified by this acceleration and the violent geometry. The hovering observer would experience a hot flux of real, intense radiation coming from the horizon.
They wouldn't see a black hole. They would see a blinding hot surface.
They would be incinerated, vaporized right at the boundary.
So the infaller experiences no drama at the crossing, validating GR. The hovering observer sees the infaller incinerated at the crossing, validating quantum field theory.
Two realities, fundamentally contradictory.
And then there's the third observer.
The distant observer, who sees only the cool, featureless Hawking radiation, perceiving the black hole as a gently glowing, low-temperature object slowly evaporating over eons.
How can physics allow for these simultaneous contradictory realities?
The answer is black hole complementarity. It's the necessary compromise that allows both GR and QM to remain valid in their respective domains.
So both descriptions, painless crossing versus immediate incineration, are correct.
Correct, but their realities are isolated. The infaller can never communicate their experience back to the hovering observer after crossing the horizon.
It's the ultimate firewall. Since the two observers can never compare notes, physics doesn't have to resolve the contradiction.
Exactly. This saves the day for Einstein's equivalence principle. but it immediately leads to the single most critical, unresolved issue in modern theoretical physics, the information paradox.
Let's explain the stakes of this paradox. If a physical object falls in, say, a book encoded with specific information, its quantum state, and the black hole evaporates via featureless thermal Hawking radiation, what happens to the book's information?
Since the Hawking radiation is purely thermal, like the heat from a bonfire, it carries energy, but no specific quantum information about what fueled it. If the black hole fully evaporates,
The information is destroyed, it vanishes from the universe?
and that is catastrophic, because it conflicts directly with the fundamental laws of quantum mechanics.
Which state that information must be preserved?
Always. Information is never truly lost, it is just scrambled or transformed. If information can be destroyed by a black hole, the determinism of the universe, the idea that the future state is uniquely determined by the past state, is fundamentally broken.
And Hawking initially said the information was destroyed.
He did, sparking a decades-long theoretical conflict known as the Black Hole Wars. This paradox is the ultimate test for unifying gravity with the quantum world.
And this paradox is the beating heart of Cox and Forshaw's argument. This profound contradiction forces physicists out of their comfort zone, seeking new theories.
Exactly. Progress in physics is often driven by paradoxes. Which brings us to Chapter 6, the sound of one hand clapping. And the key to resolving this paradox, the source material argues, is a concept far more exotic than black holes themselves: quantum entanglement.
This is the resource required to link the low-energy physics of Hawking radiation to the grand theory of quantum gravity. Entanglement is the classic example of counterintuitive quantum mechanics, famously dismissed by Einstein as spooky action at a distance.
But it's fundamentally real. It describes a deep quantum correlation between two or more particles, where their fates are intertwined regardless of the distance separating them.
So if you measure a property of one particle, you instantaneously know the corresponding property of the other.
Even if it's 2 million light-years away in the Andromeda galaxy.
This link is instantaneous, seemingly violating the cosmic speed limit of light.
Although no actual information is transmitted in a way that allows us to communicate faster than light, it's a correlation, not a signal.
Right. To appreciate how this solves the paradox, we need to think about information digitally. We deal in classical bits, either 0 or 1.
But quantum information is stored in qubits, or quantum bits, which can exist in a superposition of both states simultaneously, like Schrödinger's cat being both alive and dead until the system is observed.
Qubits allow for exponentially richer information encoding. Entanglement is the vital resource that holds these superpositions together.
Now, apply this back to the black hole. The solution to the information paradox requires that the thermal, featureless Hawking radiation must actually be highly correlated with the quantum information that fell into the black hole.
And this correlation must be established via entanglement.
So the information of the falling matter isn't destroyed. It's simply encoded in a deeply entangled structure. For the information to escape, it can't be trapped inside the black hole's volume.
It must be stored on the surface, ready to be read out through highly correlated Hawking particles over time.
Exactly. Which leads us directly to perhaps the most revolutionary concept in the book in Chapter 7, the world as a hologram.
This circles back beautifully to the black hole thermodynamics laws we discussed. Specifically, Bekenstein's insight that the entropy, or the amount of information of a black hole, correlates directly with its surface area, not its volume.
This insight forces a radical conclusion. The information describing the entire three-dimensional object that fell in is fundamentally stored on the two-dimensional boundary, the event horizon.
Like a hologram, a 2D photographic plate contains all the information needed to project a 3D image.
The principle suggests that the three-dimensional reality we experience inside the black hole, or possibly even our entire universe, is mathematically equivalent to a set of laws operating on a 2D surface boundary.
As Cox and Forshaw articulate, the inside of a black hole, in other words, is somehow the same as the outside.
It's genuinely mind-bending. Our perception of reality as fundamentally 3D is challenged. But this idea helps reconcile the contradictory observations we saw with complementarity.
It does. When the infaller crosses, they feel no drama, because the local geometry is flat. But the hovering observer sees their quantum information being copied onto the surface, the event horizon, as they burn up.
The information isn't lost, it's being mapped onto the boundary.
But wait, why can't the universe just copy the information? Say one copy burns up on the horizon, encoding the information into the escaping Hawking radiation, and the other copy falls safely to the singularity. Doesn't that resolve it?
That hypothetical scenario is strictly prohibited by one of the most robust theorems in quantum physics, the no-cloning theorem.
What does that theorem state?
It dictates that you cannot make an identical copy of an unknown quantum state. If the information of the falling object were copied, one copy exiting via radiation, one copy hitting the singularity, the theorem would be violated.
And since the physical world adheres to this law, it acts as a fundamental barrier.
You got it. Because you can't clone the information. The information cannot exist independently inside and outside the black hole simultaneously. It must be that the exterior description and the interior description are fundamentally linked.
The interior structure must be holographic, or the laws of quantum mechanics break.
And this realization that entanglement and information are essential for solving the black hole paradox leads Cox and Forshaw to their ultimate conclusion in the final chapter, Chapter 8, the perfect code.
Okay.
Quantum entanglement is not just a quirk of black holes, it is the universal weaver, fundamental to the stability and structure of space itself.
This is where we connect computation to cosmology. Entanglement has this extremely robust quality, which is utilized in quantum computing for something called quantum error correction.
Right. Quantum systems are incredibly fragile. Qubits are prone to decoherence, the loss of their quantum state. Quantum error correction is the engineering technique used to encode information redundantly across many entangled qubits, shielding it from disturbance.
The entanglement structure itself becomes the protective layer.
And the parallel to the cosmos is breathtaking. Just as quantum engineers use entanglement to ensure the stability of information inside a quantum computer, the sources suggest that entanglement may be weaving the very fabric of space-time, ensuring the stability of the space we inhabit.
So space and time might not be the fundamental arena in which physics happens.
They might emerge from the underlying network of information and entanglement.
This is the ultimate realization of John Archibald Wheeler's radical philosophy, it from bit. He proposed that all things physical are information theoretic in origin.
The universe at its core is informational. He even suggested that entanglement weaves the very fabric of space-time.
It completely shifts our classical perception. Time and space are not things, but orders of things, as the philosopher Leibniz suggested.
They are relational concepts rooted in the robust underlying fabric of quantum information and entanglement. The existence of black holes, which forced this confrontation between GR and QM, revealed that the universe is built on a perfect, self-correcting code.
So let's wrap this up. We've completed a journey, starting with the purely elegant geometry of Einstein's general relativity, validated by Schwarzschild solutions and the perfect simplicity of the no-hair theorem.
We then watched the classic picture shatter when Hawking introduced quantum mechanics, proving black holes have temperature and entropy, leading us straight into the profound contradictions exposed by the three observer frames and black hole complementarity.
This collision gave rise to the information paradox, the challenge to determinism itself, which could only be resolved by realizing that information is stored holographically on the black hole's surface.
A necessity enforced by the no-cloning theorem and powered by quantum entanglement.
And finally, the ultimate insight. The quantum entanglement required to solve the black hole information paradox may be the fundamental information theoretic code that weaves the entire stable structure of space we inhabit.
Black holes are truly the extreme laboratory where gravity and the quantum world must eventually be unified.
It's an overwhelming but unifying thought. Wheeler believed reality arises in the last analysis from the posing of yes-no questions and the registering of equipment-evoked responses. If the entire physical world is fundamentally an informational code,
then the universe functions as a self-regulating, massive computational entity. The distinction between the computer and the cosmos blurs entirely.
which leaves us with the ultimate provocation for you to mull over. If our reality, the very fabric of space-time, is maintained by a vast quantum error correction mechanism that prevents information from being lost and the geometry from collapsing, what does it mean that we, as conscious observers who ask the yes-no questions and register the responses, are also part of this perfect self-correcting code?
We are not just in the universe.
We are woven into its stability.